Just like with dynamics, we can also talk about the energy of rotations. So let's jump into that. So this works, again, very similarly to linear kinetic energy. So just like before with linear kinetic energy, we had delta KE equals 1/2 m v squared delta v squared. So now with delta KE rotational, it's still going to be 1/2, but like before, instead of m, we're going to use I, the moment of inertia, and instead of v, we're going to use omega squared. So in other words, if for some moment of inertia we change the speed at which it's spinning, it's going to gain or lose rotational kinetic energy. So here we've got a typical small rescue helicopter has 4 blades. Each is 4 meters long and has a mass of 50 kilograms. These blades can be approximated as thin rods that rotate about one end of an axis perpendicular to their length. So you can go back to the previous videos, look that up on the table, and you'll see that you get I for those rods is equal to m times the length of the rod squared over 3. So I'm just going to put that aside for later. The helicopter has a total mass of 1,000 kilograms. Calculate the rotational kinetic energy in the blades when they rotate at 300 RPMs. So we know that the delta KE rotational is equal to 1/2 I times delta omega squared. And so this will be 1/2 I times omega squared minus omega naught squared. But the initial speed is 0, so they're not rotating at all. And again, this is because technically we can't calculate an amount of kinetic energy. So when they ask us to, it's basically saying, compared to when they're at rest, how much energy do we have? So this will be 1/2 I times omega squared. Omega, we know, is 300 RPM, rotations per minute, but we need it to be in radians per second. So 300 rotations per minute. We need to get this into radians per second. Let's deal with the minutes first. So I want to cancel out those minutes, so I'm going to put minutes in the numerator, seconds in the denominator, and there are 60 seconds in 1 minute. The minute units can cancel, and so this, if I just took 300 and divided by 60, I get rotations per second. Then I want to get rid of rotations, and I want to turn them to radians. Well, how many radians are in one rotation? 2 pi, and that will cancel my rotations. So if I take 300, multiply by 2 pi, divide by 60, I get, some number of radians per second. So that'll be 5, 10 pi radians per second. So that I can come back over here. 1/2 I is m omega L squared over 3 times omega squared, which is going to be 1/2 50 kilograms times an L of 4 meters squared over 3 times a radian of 10 pi radians per second squared. This will give me, what's that, 16 times 50, 16 times 5 is 80. Yeah, so that's 800, 400. So I'm trying to do a lot of math in my head. 50, it's easier to do it this way. 50 divided by 2 is 25. 25 times 16 will be 400. 400 times 100 will be 40,000. Divided by 3 will be joules. But this is for one helicopter blade, because I did 1M, 1L, all of that. So multiply that by 4 to get the total of all 4 helicopter blades. So that's the idea here. Again, it's exactly the same as what we've done before, just using I and omega.